All right. So today is basically the last topic that we'll cover. It has to do with what happened when we start to have more processing cores on the chip, right? And the topic is called network on chip. This is basically about how do you connect CPUs together, right? A quick recap is when you access the cache, right? When you access the cache, we always assume that when you send the access to the cache, there's no time that you actually have to spend sending the data over from the CPU to the cache, right? Is this true? In most cases, in a small system, when you use a bus, this is basically really, really fast. So the assumption is almost true. But let's imagine if you look at, say, a server-grade processor or even things like the GPU nowadays, right? You have many cores on that chip. Many cores on the chip. And the problem comes when if I have to send the request from one core into another core's cache, then you have to actually get there, right? So when you want to access an on-chip cache, the data request is basically generated from the CPU core, and then it goes to the correct cache location. Why? Because when you have multiple core on a chip, right? Let's say you have the CPU right here, right? And then CPU was broken down to core 1, core 2, core 3, and core 4. And if you look at the die, right, this can be like the location of your cache, right? But the cache is now split for each location so that you can actually put in wiring and so that it can go to the correct location and so that they can actually scale and then service multiple cache accesses in parallel, right? And sometimes you can be private to someone else's core, right? So the shared cache, the model basically means that it spans across multiple nodes on the chip. Now you think of this island, right? Because now your cache is also becoming its own island. And you basically need to make sure there's a way for you to connect everything in here, right? You need, so the goal is, first of all, you will want to make sure you can connect the components here together, right? So that they can communicate and send data from one place to another, right? And then when you want to access each of these caches, in the end, now that you have this network of things, it means that they will take a different amount of time, right? So now we'll talk about different type of interconnection network, from the most basic to the more complicated ones. And let's start with the most basic one, the bus, right? How many people heard about the word bus in the computer? Anyone heard about this word before? Oops, not trying to zoom in, sorry. All right. Anyone heard of this word, bus? Basically, think of a bus as, yes, thank you. Think of it as a wiring where if I want to use the bus, no one else can use it. If I want to use the bus at this cycle, no one else can use it, right? So bus interconnects is, imagine like you have one single bus that connects from one place to another, right? If you want to use the bus, you have to wait at the bus stop until the bus arrives for you, right? Until the bus arrives for you so that you can go from one place to another. And this is basically, if you envision that scenario, this is basically the only bus that can move things around, right? So as you guessed, this would work well if you have one core. This actually works pretty well when you have two cores. If you look at dual core machine, bus is good enough, right? If you have four core, now it gets questionable. It gets questionable. Why? Let's say you have a core that are like this: core 1, core 2, core 3, and core 4, and they share this single bus that connects them to the L1 cache. What does it mean? If I have a load instruction here and here and here, right? I want to access data for core 1, core 2, and core 3 just suddenly at the same time. The problem means that I need to wait. One of these will be able to use the bus, the other two have to wait. So that's the problem, right? In the CPU, the bus basically connects two locations together so they can send data, right? But it's really simple, but it is also really restrictive, right? So here is the benefit. It's really cheap to implement. It's simple and cheap to implement, right? And then the downside is it can take some time if the bus is long, right? If the bus connects multiple locations, then you have to wait for a while, right? So in the end, it's not really scalable, especially when you want to increase the number of cores, right? And now you have the Minicore Era where you can have a processor with 4 cores, 6 core, 8 core, 12 core, 16 core, 32 cores, and 64 cores and more, right? You're looking at many cores on your CPU. And you cannot really just use the bus because if you want to connect 64 different locations with only one single bus, then you're basically screwed, right? If you want to send data to the cache, you have to wait a lot, right? So now the network on chip comes to the rescue. Basically, the design was basically inspired by computer network, basically. The idea is, hey, why don't we build a network that connects the resources on the chip, right? So if you want to connect things together, one of the simplest thing you can do is to connect them in a ring, right? So the simplest form of the way to connect is, well, let's use some network topology to connect the CPU core. And let's use a ring. So that's the next simplest one. This is actually common in like Intel and AMD CPU for the desktop, right? For the desktop, let's say you have 4 core, 8 cores, the ring is good enough. The way it works is like this. So if you, let's say you have 4 core 1, core 2, core 3, and core 4, it would connect each other like this in a ring. Basically, things would get connected in a ring, so you can send the data to your neighbor. So if you want to send data from C1 to C3, you would go through C2, then C3, or C1, C4, and back to C3, right? You have the clockwise direction, and you have the counterclockwise direction in order to send the data from one place to another. And each link here is basically a bus that connect the two sides together. There's a bus that connects C1 and C2, and then the bus that connects C2 and C3, and so on and so forth, right? And each vertex here is called a node, which has its own router. Why does it need its own router? Because you need to be able to tell, okay, this packet coming in, where's your destination? Where should I forward to? Should I go to the clockwise or the counterclockwise direction, right? And the node can be just the CPU alone, CPU and some slice of the cache, or the memory controller, or a cache with the controller. For example, the GPU would assume that you have the cache and the controller together, right? And then that's about the topology. Topology is how you connect the node together, and we'll talk about a few more topology in this class. Then the next thing is, you might have heard about the word packets, right? Can someone define what is a packet? Can someone help me define what's a packet in the network? So what should be in the packet? I know some of you are doing in a computer network lab. You need to be able to answer this question. Let that answer come out. Come on. ใครลูกศิษย์อาจารย์บักเราตอบแล้วแพ็กเกจคืออะไรครับหรือผมยังอยู่ใช่ไหม so what's the packet
แพ็กเกจเหมือนเอาข้อมูลไปยำรวมกัน แล้วก็ส่งไปทีเดียวนะครับ
โอเคมันก็เหมือนแพ็กเกจเวลาเราส่งของนะส่งของเนี่ยเราต้องใช้อะไรบ้าง ก็คือของที่เราจะส่งใช่ไหมฮะของที่เราจะส่ง มันจะอยู่ในแพ็กเกจ ก็คือแพ็กเกจที่เราส่งเนี่ยก็จะมีของ มีอะไรอีก
มี address นะครับ
มี address ถูกต้อง ก็คืออยู่ใน header ก็ว่าไป บอกว่า จะส่งไปที่ destination ตัวนี้นะ แล้วมีอะไรไหมฮะ
แล้วก็มีตัวเช็คตัวหนึ่งว่าที่ส่งไปถูกหรือเปล่า
ก็คือมีการมีวิธีในการ verify ว่า packet เนี่ยคือสิ่งที่ต้องการหรือเปล่าใช่ไหม เพราะฉะนั้นคอนเซปต์ของ packet ใน network Onship ก็คล้ายๆกัน so recap in English basically packets has the data that you want to send with some additional information about the data. For example, where's the packet coming from, where's the destination it has to go to, and then any additional information to verify the packet, right? The problem with packets inside the ship is if you look at for example this bus, right? These are actual like wire. So if I want to send a lot of data, it means that I have to use a lot of wire to send them over. So the idea is instead of sending one single packet, you would break the packet down into multiple flits. So basically when I use the word flits, it means that when you generate the packet, the node generate the packet and say, hey, I want to access the cache, right? Data packet is big, so it doesn't always fit in the link that connect them together, because otherwise the link consumes way too much energy and you don't want your CPU to consume too much energy. So generally, packet is then broken down into multiple flits. For example, in a CPU, right, where the cache block is 64 bytes, generally then you would break the packet, the 64-byte packet, down into eight bytes data flits. Basically, now your data is going to look like this. So this is your packet, right? You would have some header, right? And you have the data in here. And then you would then break the data down into flits, right? So each one of these boxes are a flit. And when you send things over, you send first the header, followed by the first piece of data, second piece of data, third piece of data, and so on and so forth until you everything arrive at the destination. So basically, when you route things through the network, you route flits, not packets. All right. Then after you talk about the flit versus packet, now you know that things are being sent from one place to another, right? You also have input and output ports. So each of these links requires buffering that takes in the input port, right? So this is input. And then another set of buffering that would get managed, right? Where you have the output. So you would output here, input from here. You also have the input from this direction, right? Input, for example, here. And then another output that would go in the clockwise direction, right? So in this case, these are the input and output ports. Each of these ports can take in one flit per cycle. So I just take in one flit per port, per direction, generally. And you can change this with different hardware design. So this is basically flexible to some extent, right? In a ring topology, how many ports are there? You have one port on this side, the other port on this side. So there are two ports, the clockwise direction and the counterclockwise direction for the inputs, and then two additional ports for the clockwise and counterclockwise output port. So you have two input ports, right? And two output ports for a ring topology, because that's how you can manage the ring. Now let's talk about something a little bit more complicated. We call this 2D mesh, right? The word probably suggests the shape, right? A ring is probably not scalable when you look at future generation of CPU. I think for the desktop chip, they use one ring. If I recall correctly, last time I checked, the NVIDIA GPU used 3 like 3 mesh ring. Basically, it's 3 rings connected between each other, right? That would make it more scalable. But once you go through a design where you have many cores, a ring might not be scalable anymore. Like one single ring. So people come up with the ideas. Maybe we can do a 2D mesh, right? Each node has the north, south, east, and west port, right? And then you connect it this way. In this case, you're looking at a 16 node system. It can be a 16 core machine, right? And now you have the north, south, east, and west, and they can connect in this way. So if I want to send a location from here down to here, right? How many hops is that? 1, 2, 3, 4, 5, 6. Which means that I spend 6 times jumping from the source to the destination, which is actually much better than a ring that connects 16 nodes together. Because if you look at a ring, right, for 16 nodes. So let me ask this first question. What's the maximum number of hops that you can run into if you connect 16 node ring? And someone tell me that what's the longest distance I have to go through if I connect 16 CPU core with a ring? What's the longest distance? It's actually, I think 7. Because you have 15, basically you have to go through, if you go through 8, the other side, if you go the other side, I think it's 7. So I think the maximum hop is 7. But I may be wrong because let me think. So 16 node. But let's just look at this diagram, right? So you go to here, down to here, down to here, down to here, right? That would be a ring, right? So if you want to go from here, 1, 2, 3, 4, 5, 6, 7, 8 to get to this destination. If you go here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, my bad, 8. 8, actually 8. My bad, I did it wrong. Okay, sorry. It should be 8 hops. So you go then 8 hops to the destination, and you can see that the number is, well, 8 is greater than 6. So as you scale the number of core, the maximum hop for a 2D mesh is going to get a lot better, right? That also includes the average number of hops. It's going to get actually way better. It's going to get way better, right? Now let me give you an exercise. Average hop for 16 node mesh, 2D mesh versus a ring. All right. This is an exercise, and how about I make it more interesting? I will ask this on the exam. All right. I just told you one exam question. Give you the average hop for 16 node 2D mesh versus a ring. Okay. Maybe I'll just make it extra credit. Actually, just put it as an extra credit toward the end. All right. Okay, so now the next topic I have to touch is, now that you have this topology that connects things together, right? And you have a choice of, do I go north, south, east, or west? Then the next thing that I need to think about is, how do I route packets, right? Because with a network, you need a routing policy to move packet from source to destination, right? Because if I'm here at the source, and this is the destination, right? There are many paths I can take. I can go from here to here. 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 I can even go this way, right? There are many ways you can go. So now let's do a quick break. And then now that we talk about topology, we talk about ring, we talk about 2D mesh, then we'll talk about routing after the break. So let's do a 5 minutes break. We'll resume at 10, let's say 20, 22, 23. Is that okay?